Hello everybody, my name is Titus North. I'm the Executive Director at Citizen Power, and this is another one of our series of presentations on energy. Today's topic will be wind, the power of wind. Why wind? Well, wind is actually coming on very strong. It's a clean source of energy, it's safe, it's renewable. It's a way of the United States gaining energy independence. We don't have to depend on foreign sources of wind. There's plenty of wind right here in the United States. It reduces our vulnerability to volatile energy markets and to unreliable sources of foreign energy. It is a non-polluting source of energy. It is a job creator, and it is something that can potentially ease the burden on our electric power grid if we develop it the right way. Okay, what are we going to be doing today? Well, we're going to try to become familiar with the wind power capacity in the United States, in Pennsylvania, and around the world. We're going to look at different wind turbine technologies. We're going to look at the different variables that can affect the performance of these turbines. We're going to look at various issues related to the development of the wind power industry. We're going to see how wind power can be a valuable resource in the classroom, and how you can teach lessons in science and in math utilizing the issues, the concept that you're going to learn today around wind energy. We're going to, later on in a separate presentation, we will show you how to construct your own wind turbines that you can use in the classroom. And we'll talk about how wind can help us move forward and build a brighter future. Now what you see here, this is a graph of global installed wind capacity over this 15-year period from 1996 to 2011. And you can see at the end of the last century, there was really very little installed capacity. And then, if you live in Pennsylvania, you might have noticed around 2000, 2001, if you're driving along the turnpike between Philadelphia and Pittsburgh, you would see in Somerset County some wind turbines visible from the turnpike. That was just the start of things, and wind has come on strong in Pennsylvania, but that's just a small part of it. It's been growing in other states, especially Texas and the Great Plains states. This is for the entire world. It's been big very big in Europe, and now China is coming on very strong. And so you see this geometric increase. So as of 2011, you're talking about over 230 gigawatts of installed capacity. Let's look at the leading countries. So China is now out in front, and this is different from even just a few years ago. China has huge plains in the western part of the country and great wind resources. The United States also has great wind resources, as we're going to see later. Germany is a very small country, but you see they're very serious about it, and they've taken advantage of the resources that they have in their small land area. And in fact, then they've gone offshore, and they have some offshore resources as well. So we have this 46 gigabytes of installed capacity, and it's coming on very strong. In fact, in the year 2012, there was more wind generation installed than there was any other type of energy resource, even more than gas. And of course, we're in the middle of a gas boom here in the United States, but there was even more electric capacity installed that was based on wind than on gas. And it's becoming more efficient, it's becoming more cost effective. You see that the average price in 1979 was 40 cents per kilowatt hour. That's been cut to about 1/8 of that level, so now it's 5 to 6 cents per kilowatt hour, and it's very competitive with other forms of electricity. Now, here's a map of the United States and its wind resource. And what you see here, the dark blue and the bright red and the purple, blue is the best wind. And so what you'll see is the best, our best wind capacity or resources are offshore, here of Northern California and Oregon. And then the red, of course, is next best. And you'll see that pretty much the entire Atlantic seaboard has red along it, and the same with the Great Lakes right here. And then these other areas, this area in the middle of the country, from the Dakotas down to Texas, this is in the Great Plains, in the prairies, we have excellent wind resources. It's often referred to as the Saudi Arabia of wind, because we could power all of our electric needs from these states right here in the Midwest. Well, why don't we do it already? Well, the problem is that if you're talking about wind resources in the Dakotas and South Dakota, North Dakota, Kansas, Nebraska, this is not where the bulk of our population is. Our population is on the two coasts, in the South and in the Midwest. And so the issue is, how would you get the electricity generated in the Great Plains states to the population centers? It's possible, but it would require a substantial investment in our electricity grid, and an investment that really needs to be made anyway, but that we have been slow to take on. This is a very interesting graphic right here. This shows the year-end wind capacity, the wind capacity by year in the various states. You can see that California and Texas have been leaders. Texas actually, in the past few years, has just leapfrogged out in front of everyone else. But you have other states in the Midwest, places like Minnesota, Iowa, and the Dakotas get a great deal of their energy already from the wind. We'll let it run through one more time. Here in Pennsylvania started, and you're seeing, even though our resources are not as good as the Midwest, you're seeing a great deal of investment, and it's locally produced energy. And if it's produced locally, then it's less burden on the transmission grid. All right, and this is as it is today. Here's our Pennsylvania map. And you'll see that where are the resources? Well, right up here along Lake Erie, the Great Lake, and then through the Appalachian Mountains. Coincidentally, the same areas here through the Appalachian Mountains is where you find the natural gas boom, the Marcellus gas. So you have these two energy resources that are pretty much in competition with each other. Here's a map now of the existing wind farms. We have in green the existing wind farms, and if you're traveling along the turnpike, as I mentioned, you pass them up right here in Somerset, and so there's a great deal here. They're building, or at least planning more, in the east, also in the mountains. So the mountain passes tend to have strong, steady wind, and that's the right type of wind for generating electricity. Now, we're also reaping some economic benefit from the manufacture of some of the components that are used in the wind industry. And right here what you're seeing is Gamesa, which is a Spanish company. They've established a factory in Evansburg, Pennsylvania, near Altoona. And here you see the workers, and they're making the blades. And the blades of these turbines are absolutely huge. You can see that if you're at the fat end, at the base of the blade, you could walk right inside of it. And it's really something if you're traveling along the highway and you see a truck carrying one of these blades. Okay, let's get some of the basic nomenclature down. People commonly refer to these wind turbines as windmills. Technically, a windmill is a machine for turning the wind into mechanical motion. And of course the Dutch used them for grinding grain, thus the term windmill. These windmills can also be used for, say, pumping water or other, which was very common in the American Midwest 100 years ago. A turbine is a machine that turns mechanical energy into electricity, and so this is what a wind turbine does. The wind makes the blade turn, which pulls the rotors in the turbine around and produces electricity that way. Okay, so there are a variety of sizes and shapes of these wind turbines, and we'll be talking mainly about the very large utility scale wind turbines, but there are smaller wind turbines that can be used for community purposes or even by individuals. So let's look at some of these. We have very small turbines, something that an individual who's living in the right area might want to put on their own property. So here you have a small turbine that can produce somewhere between 10 and 100, 20 watt, anywhere from 20 watts to say 100 kilowatts. There are others that are larger. Here you see one. This would be a homestead, and then a fairly large turbine. This is a 50 kilowatt turbine, and so that would be on the larger size. And these might be used in rural areas. They're not really very useful inside the city because you don't have the strong, steady wind in the city that you would want because of all the buildings. Let's move on to some types of applications. So you can use a wind turbine for off-grid water pumping. Here you're using an electric pump, but the electric pump is powered by electricity from this turbine. And the advantage here is you don't have to bring the grid out to the electric pump. You can produce the electricity right there where it's needed. Here we have supplementing grid power. So this looks like a school here, and it's got a turbine in front of it. Citizen Power was actually involved in a turbine project at the State College School District, which put a experimental turbine on its property, and it generates power for one of its schools, or at least some of the power. And so this is something where you can, if you're in the right area and you have the right kind of wind, you can generate some of your own electricity, just as some people are already doing with photovoltaic solar cells, solar panels on their roofs. And these are other pictures from somewhat larger installations. What you'll see in this picture, this looks like a typical, say, northern Canadian town, something that you might find in northern Saskatchewan in the Canadian Shield. And it's very difficult to bring the grid to these isolated communities. And to the extent that you can produce your own electricity, then it's very valuable indeed. Net metering is something that you might be familiar with. This is something, if you have your own electricity generation capacity on your property, you can take advantage of net metering. It's very common with solar panels. People who have solar panels on the roof, when they're producing more electricity than they are using, then they can sell that electricity back to the electric power company. And typically, if in some areas, like in the Pico area, if you're in Philadelphia, you would have two meters at your house. One measures the electricity going out, and the other measures it coming in. Other areas, the meter will simply run backwards when you're producing an excess of electricity. Now, for the large utility-based turbines, and this is what's really been coming on strong. And when we were talking about the huge geometric increase in wind electricity generation capacity over this past decade or so, this is really what we're talking about. And these wind turbines are very, very large indeed. So if you look here at this picture, here's Lady Liberty in New York Harbor, 305 feet. A very typical wind turbine that you might see in Somerset County here in Pennsylvania would be that much taller, 328 feet. In Europe, they're building even larger ones. This is one that is 650 feet, so it's more than twice as tall as the Statue of Liberty. The blades are long, and there's two reasons for getting high. One reason for getting high is because the wind is steadier and stronger higher off the ground. But also, if you're going to have very large blades which capture more wind, you need to be higher off the ground. So a typical wind turbine, if it's 450 feet tall, then it might have blades that are over 100 feet long, and its foundation might be 20 feet deep. And we're talking about turbines that could be, say, anywhere from 1.5 to 5 megawatt in terms of their capacity. Okay, so wind farms, they really are the crop of the 21st century. The turbines that I've mentioned a few times already in Somerset County by the Turnpike, they're on a dairy farm. And we have visited the dairy farm, and the cows don't seem to mind. The turbines take up very little space. There's just the base there. They don't require a lot of infrastructure around them. They don't cast much of a shadow, and so they're not interfering with growing crops. They don't block out the sun. This is something that can be very easily integrated into existing agricultural communities. They also can be located offshore. Now, we don't have offshore wind in the United States yet. We don't have any generation yet. There have been proposals and plans for some. There's a proposal for offshore wind off Cape Cod. Some of the tourist industry has raised a fuss about it, and so it has not gone forward. But this is I believe in Holland. This is a wind farm offshore, and you can judge for yourself whether you think this is aesthetically pleasing or not. But offshore is where the very best wind resources are. And you'll see that 11 countries already have offshore wind farms. The United Kingdom is the leader. The United Kingdom has a great deal of offshore wind farms in the north of the country, off the coast of Scotland in particular. You'll see Denmark. If we look at the list here, we have Denmark, Netherlands, Belgium. These are all along the North Sea, which is very windy. And then further down the list, you see China's developing them, Japan's developing them, and the United States will be on this list. In areas where the turbines, when they're offshore, they're typically pretty close to the coastline because they're built down into the bottom of the sea, into the bedrock under the sea. But what if they could be moved further offshore? Well, here are some ideas for having them float or be tethered to the bottom of the shore, where you don't actually have to sink concrete into the bedrock at the bottom of the sea. All right, let's talk about the actual composition of a wind turbine. So the main parts that you see from the outside, we have the blades, the hub right here, and the hub, and then the rotor would be in here, and of course you have the base or the tower. So these are your main components. Of course, inside this part, it's called the nacelle, which is, if you're a Star Trek fan, the nacelle was the part of the spaceship where the people and everything was located. The nacelle it's a French term referring to a boat, and this is where the guts of the machinery are located. And so you'll see lots of gearing. The gearing is very important because you can ramp up say a typical turbine might spin at about 12 to 15 times per minute, you can ramp that up to thousands of RPM using gears, and that is better for producing electricity. Here are some of the gears inside of the turbines, inside the nacelle, and these are very huge pieces of equipment. And the manufacturing is it's a big deal. It's a big business, and there's a great deal of job creation potential there. Okay, here are some other technical issues. You want these turbines, these horizontal axis turbines, to be facing into the wind, and of course the wind doesn't always blow from the same direction. So you need some sort of mechanism for turning the turbine so that the blades will be facing into the wind. This can be done two ways. You can have a passive system, and this is typical on smaller turbines, where you have this stationary blade in the back that keeps it facing into the wind. It's a tail vane, and then on the larger utility-based turbines, you have what's called an active yaw. The yaw is facing into the wind, and they have detection devices on the turbines that detect where the wind is coming from, and mechanically will turn the turbine into the wind, and so that they produce electricity at the optimal rate. Okay, now how about how the wind works? Well, wind is really just another form of solar energy. What happens, and this is a very simplified explanation, but you have the sun which heats up the earth every day, but it doesn't heat the earth evenly. Where you have cloud cover, for instance, you're going to be getting less solar energy at the surface. That heats the air and it heats the ground less than in unclouded areas. And where you have the colder air, the air is going to be sinking. It's going to create a high pressure system. Conversely, where the sun is shining directly, the surface of the earth is warm, and you get air rising. It creates a low pressure system, and the wind blows from the high pressure to the low pressure areas. Now, as I've mentioned before, what you want for wind turbines is steady wind. What you don't want is turbulence. So if you've ever walked down the street in Chicago or New York on a windy day, and you see these little whirlwinds of turbulent air, and it blows off people's hats, that might be very dramatic, but that's not the kind of wind you want. What you want is a steady wind. And turbulence is created very easily by trees, by houses. And so in order to avoid the turbulence, there's a couple of rules of thumb. You don't want to be, if you have a house, and the house is height H, you're going to have an area of turbulence that's going to be twice as high as the house, and it's going to continue for about 20 times the height of the house. This is why you'll find the turbines offshore, where there are no houses and no trees, or in the Great Plains states, where everything tends to be pretty flat, or otherwise in places like Pennsylvania, which are neither flat nor open sea. You'll find them on mountain ridges where whatever trees and houses there are down below. So you want to have the turbines high enough so that they're taking advantage of this steady wind. So the amount of energy you can derive, amount of power that you can derive from the wind, is a factor of three things. It's a factor of the area that your blades are sweeping through, which is pi r squared, r being the length of the blade, the wind speed, and the air density. And we have this formula right here. So it's 1/2 rho, which is the air density, times the area swept, which is pi r squared, times the velocity of the wind cubed. Well, obviously the velocity of the wind is the most important factor because it's cubed. So the difference between a 5 mile per hour wind and a 10 mile per hour wind is not a factor of 2. It winds up being a factor of 8, which is 2 cubed. So you really want the higher winds. It makes a big difference, and you want them to be steady. Here is a humorous sign from Wyoming. It kind of illustrates this. If this is a windsock, and if the windsock is hanging straight down, it's broken, because you're always going to have wind in Wyoming. If it's at 30 degrees, it's a fresh breeze. 45 is a gentle zephyr. 60 degrees, that's hurricane. 75, beware of low-flying trains. 90 degrees, welcome to wonderful Wyoming. Okay, and now earlier I mentioned if you've ever seen a truck that's carrying one of these wind blades to its site where it's going to be put on a turbine, it's really pretty impressive. Here we have a picture of a truck carrying one of these wind blades across a bridge, and that's how big. Here's the head of the top. The tractor of the truck just looks tiny compared to this blade, and there are blades that are even bigger than this. Now, you cannot capture all of the wind. You cannot utilize all of the energy of the wind that is passing through a turbine, because some of it does have to pass through. There is a theoretical limit called the Betz limit. So no matter how well the turbine is going to be designed, and the blades are going to be designed, you're going to get at least 40% of the energy of the wind is going to pass through. You can't capture 60%. So you're going to be capturing less than 60%. That's a theoretical limit. And modern wind turbines typically get somewhere between 35 and 45% of the energy passing through them. The blades themselves, in order to maximize the amount of energy that they capture, tend to be shaped in an airfoil, very much like the wing of an airplane. This produces a lift effect and helps them turn faster. So what are the blades made of? Well, you might think that they're made out of aluminum, like an airplane, but you'd be wrong. Actually, having the constant torque from the being turned would fatigue aluminum, and so what's better materials are wood. Wood's used especially for the smaller turbines, or for the larger turbines it's typically fiberglass, which is lightweight and strong. Okay, here are some concerns that are often raised. How noisy are these turbines? Will they bother my neighbors? Are they an eyesore? And do they have an impact on the wildlife? Okay, well, first of all, let's compare this to other sources of noise in our modern world. Jet airplanes obviously make a lot of noise if you're around the airport. We have, pneumonic drills, other industrial noise, something very common in a lot of houses, at least used to be common in houses with teenagers, the stereo music. I guess the headphones have taken care of some of that. But there's a lot of noise. A turbine, of course it depends where you're standing, but turbines don't make that much noise unless if you're right up to them, you can hear them, or acoustics can be kind of tricky things. Sometimes you might be familiar, if you live anywhere near train tracks, you might be familiar with the phenomenon of being able to hear the trains at night but never hear them in the day. It has to do with the acoustics, and it has to do with how air travels through through hot air and cold air and things like that. So I have the personal experience of seeing a turbine up on a hill and stopping it and wanting to take pictures of it. And so I pulled my car off the road, and on the road you can hear the cars when they're passing, and we hear a lot of sound from cars. I had to get really close to the turbine until I could hear the turbine over the sound of the cars. So in general, they're really not going to make that much noise unless it's very poorly situated, very close to someone's house. It's not that much of a source of noise. What about the visual impact? Well, if you're not used to them and you see a turbine, it's an impressive structure, and it'll capture your attention. On the other hand, we have these imposing structures around us that we completely tune out. Telephone poles we tune out, radio towers, cell phone towers. Those popped up all of a sudden, but people aren't, and they're ubiquitous. They're all over the place if you actually keep an eye out for them. And these water towers, of course, that water utilities use. These are things that we've just come to accept and hardly give a second thought to. And so certainly a turbine could be the same way, and some people think they look kind of neat, as a matter of fact. And then, of course, if you don't have the turbines, you need to have more of this. And so which would you rather have? Would you rather have, this is an artist rendition of the Cape Cod wind farm, the offshore wind farm, where you might not be able to see this very well in your video, but offshore you can see this long line of turbines. Or are you going to have the smokestacks of say a coal generating plant, or perhaps a nuclear generating plant, and the potential disastrous effects if there's a meltdown? That leaves us with the third concern. What about the wildlife? What about the birds? Wind turbines got a bad reputation in the 1980s from the Altamont Pass wind farm in California. This was one of the earliest large-scale commercial wind farms, and so there was a learning curve. And as you see from these turbines, the bases, instead of those smooth, white, solid bases that you've been seeing on all the previous slides, these had a steel lattice tower that would support each turbine. Well, this provided areas that a lot of birds thought would be great for building nests. Consequently, a lot of birds, in particular the large raptors, started building nests in these towers, and they fell victims to the blades. Another problem was that, of course, these were situated on passes that were very common for raptors, that this is a big raptor area. And then to further complicate things, these did not have the advanced gearing systems that I talked about earlier. Consequently, the blades were turning much faster than they do now. I mean, so the blades that you will see commonly now might be turning somewhere between 12 to 15 times per minute. These were going several times faster than that, and therefore more dangerous to the birds. So, and some of these turbines are still in use, and so when you see statistics on bird deaths from wind, in particular from raptor deaths, it's almost entirely from this wind farm. The other wind farms are much more environmentally friendly, at least for the birds. And so you will see this is a chart of avian deaths per year, and this was from a study by Erickson and Company. They found that glass windows were actually the largest human caused cause of death for birds. Electrical transmission lines were next. House cats and hunting, automobiles. You see them by the side of the road. Wind turbines were completely insignificant. I will say that there's another issue of wildlife, and that's bats. There was a study in Pennsylvania where this was just in 2011, 2012, and they found that by turning off the wind turbines when the wind is blowing less than 5 miles per hour, eliminated the great majority of bat deaths. And of course, when the wind is turning less than 5 miles per hour, it's only producing minimal electricity. So in order to eliminate over 90% of the bat deaths, the owners of the wind turbines only had to sacrifice something like 1 or at most 2% of their electricity production. So it's a pretty good trade-off. So why have wind education in K through 12? Well, it's a great vehicle for teaching students valuable lessons in math and science. It encourages a higher interest in science and math. And you can also pull it into other areas where you're talking about the environment, you're talking about wildlife management, and it's also, if kids get interested in the wind, there's a great new industry of jobs and careers in the wind industry. So some of the jobs would include engineering jobs, design, computer programming. There's jobs in the environment, environmental impact assessment, meteorology. There's manufacturing and constructing the wind turbines. There's operation and maintenance. And how many of you have students that you could imagine climbing on top of one of these wind turbines? I know I've met a few students like that in my career. There's development, public relations, financial, legal, marketing, sales. So here are some of the things that the wind can help you teach about. You have scientific processes. There's the use of simple tools and equipment. Forces causing change. Energy transformation, so mechanical energy being transformed into electric energy. Circuits, principles of electricity and magnetism. Weather and meteorology and climate. And issues of energy, in particular renewable and non-renewable energy. You have math lessons. You could build math lessons around tip speed ratios, calculating heights using triangles. So you have trigonometry, coefficients of power, the swept area, the pi r squared, with the length of the blade, the gear ratios, the power calculations, the capacity ratios. And then also, in another video, we'll be showing you how to build your own model wind kits, working model wind kits. And you can see how many volts you can get out of one of these kits. And it's amazing. We've had over 1,000 teachers go through our training courses, and the teachers have done pretty well, but the best results we got were from a 8th grader who was able to better all of the teachers who had gone through our course. So you never know what you're going to find. Some of those kids out there we're going to be relying on them to be building these next generation of machinery, and while they're at it, maybe paying into our Social Security. There's all sorts of fun you can have. So here we have some fun-looking designs. Almost look like something out of Monsters, Inc. maybe. But you can experiment with all sorts of different things. Thin blades as opposed to thick blades. Multiple blades as opposed to 2. All sorts of things with the base and the blade shape. And when you get down to it, wind energy in the classroom is just fun. I think these guys' faces say it all. Well, I'd like to thank you for joining us on this presentation on wind energy, and I hope you'll get some good use out of it. Please check out our video on how to construct the wind turbines and our other videos in this series. Thank you very much.